before in this form as function times dz. And holomorphic just means that the coefficient phi of z varies holomorphically with the local variable z. This can be defined on any on general Riemann surfaces, but I'm going to focus only on the case where the surface is compact. So just for simplicity of the presentation. Now, if you have, now what I'm going to do next is to try to explain part of the structure that comes attached to this definition. So the first thing is that if you have an abelian differential, then you can always locally construct what one calls natural local coordinates, which are special coordinates of the Riemann surface that make the expression of the form as simple as possible. So if you have a point P, which is not a zero of the abelian differential, then you can define a new local coordinate zeta in this way. And then if you write the abelian differential in this coordinate, it simply becomes d zeta. It's slightly more complicated if the point P is a zero, say of multiplicity m of the form. In this case, you should use this formula. And then with respect to this coordinate, the abelian differential will be written just like that. So you can make, these are coordinates that make the differential as simple as you can possibly want them. And the point with these coordinates is the following. Just focus on the case where the point P is regular. So on a neighborhood of in an open set where the differential form does not vanish, then of course there's more than one possible choice of a natural local coordinate. And the key point is that if you take different choices, they give you different local coordinates, and the change of coordinates is done by translation. So if you have zeta prime, which is another natural local coordinate near the point P, then the change of coordinates between the two is given by a translation. So it's like having a surface. When you define a surface, you ask it to have local coordinates, and the change of coordinates should be a smooth map. In this case, it's much more than a smooth map. It's just a translation. And this thing you call a translation surface, and the set of all these local coordinates you call a translation atlas. I'm focusing really on the case, the neighborhood near regular points. Of course, singular points require slightly more detailed analysis. Now, so this is the notion of a translation surface. And once you look at the definition, you immediately realize that it has more than meets the eye. A translation atlas always defines on the surface a flat metric, which is just taken from the plane to the surface via the local coordinate. And it doesn't matter which local coordinate you choose, because the changes of coordinates are translations, and so they respect the flat metric on the plane. So a translation surface comes with a flat metric. And it also comes with an extra structure, which is a parallel vector field that does not vanish. I call it the upward direction. Just think of the positive imaginary axis on the plane, bring it to the surface via some local coordinate. That's what I call the upward direction. And again, it doesn't matter which local coordinate you choose, because you get the same thing. So translation surface is a Riemannian surface with a flat metric, away from the singularities, away from the zeros of the differential, the abelian differential, plus this upward direction. And it's not difficult to see that, conversely, if I give you a flat metric and such a vector field, then this describes completely the translation surface. So another way, I've given you three definitions of an abelian differential. It's a complex holomorphic one form. It's a translation surface. It's a Riemann surface with a parallel vector field that does not vanish. All this outside a finite number of points that are singularities. Okay. I also want to give you a picture so that you can visualize translation surfaces. So here is a geometric construction of a translation surface. You just take a polygon on the plane with a finite even number of edges. And besides, the edges should be organized in pairs. In this picture, I've colored the edges according to the pairs. You have two red edges there and there, which are parallel and have the same length. And it's the same for the other pairs, the blue ones, the magenta, and the green. So take a polygon with an even number of sides, and the sides being organized in pairs of segments which have the same length and are parallel. The simplest example would be a square where opposite sides have the same length and are parallel, and you know quite well that if you take a square and you identify opposite sides, then you get a surface, which is a torus. So here is a generalization. Take any polygon with these characteristics, identify sides that belong to the same pair by translation. What you get is a translation surface. The structure of this translation surface comes from the plane, the atlas and the flat metric, and so on. The singularities are points that lie where the vertices, at the points that come from identification of the vertices. Well, one interesting observation is that actually this is not one special way of constructing a translation surface. Any one can be constructed in this way. But this observation is slightly misleading because there's no uniqueness. So you should think of this as a good way to draw pictures, but please keep in mind that different polygons can give rise to the same surface. For instance, if you take this polygon and you cut it along, say, this segment here, and you take the part on the right and bring it here, glue along the red side, then you get a different polygon with obviously the same surface. So one of the things that one would like to understand is, since this object has a Riemann metric, one would like to understand the behavior of this Riemann metric, the behavior in particular of its geodesics. The geodesics look very simple because they are just straight lines. This is a flat surface, but it turns out that it can actually be quite rich, and we are going to see that because of these identifications. So I've tried here to suggest the setting of the problem. We are going to basically to fix one direction in this surface, to consider geodesics leaving from a generic point z in this direction, and we would like to understand how this geodesic behaves. For instance, in the torus, in the flat torus, if you do this, then you know what happens. If you leave in one direction going forward along straight lines, then it all depends on the slope. If the slope is rational, you are going to come back to the same point, which means that the geodesics in this case are closed. If the slope is irrational, then you never come back. The geodesics are dense. They are more than dense, as we are going to see. And that's the kind of issues that one would like to understand in general. So you see, this is, if I formulate it in this way, it's a problem in differential geometry. It's also a problem in complex analysis because geodesics of this metric are what calls trajectories of the Abelian differential. And they have a meaning in complex analysis. Namely, they describe directions in which one can deform the complex structure. And I will try to convince you that this is also a problem in topology because this is a particular case of a structure that is called measured foliations. So it goes like this. Take a surface, fix one direction. In this case, in the picture, the direction is represented by a choice of an angle theta with respect to the vertical. The vertical is this upward direction. You fix theta. You leave from any point along the geodesic which has this angle to the vertical. This splits the surface into leaves, into curves, the geodesics along this direction. So this gives you a foliation, and this foliation is special in that it is defined by the kernel of some real closed one form. I actually wrote the real one form there, the real part of e to the I theta, the same theta, times omega. That's the real part is a real closed one form, and the leaves are tangent to the kernel of this one form at all points. That's what it means to say that the foliation is given by this real closed one form. Now, Thurston called this kind of foliations measured foliations, and they play a role in what is usually called Thurston theory. So if we are able to understand geodesics on a translation surface, we are giving some understanding of measured foliations. And it turns out that this some understanding is not so small, because lots of measured foliations are actually realized by geodesic directions in the translation surface. There are many ways to state this, and in some sense the statement is quite classical, going back to Calabi. I'm just writing one part of a more recent formulation by Konciewicz and Zorich, which says that if you have any measured foliation with a certain finite number of singularities, and assume that there are no leaves going from one singularity to another, so assume there are no settled connections. This is a sort of a generic assumption on the measured foliation. Then this measured foliation can be written as a geodesic foliation on some flat metric, on some translation structure on the surface. You can find the metric, you can find the translation atlas, so that the foliation is actually corresponds to geodesics on this, with respect to this metric. So by understanding trajectories of abelian differentials, one is also giving a good deal of understanding of measured foliations. So the way we are going to do this, at least try to give some progress in this direction, is by exploiting the fact that the space of abelian differentials, now I'm going to parameter space. I'm going to look at the space of all abelian differentials. And this space itself comes with dynamical systems that act on it. One particular dynamical system, that's the Teichmüller flow, that we are going to exploit. So just to introduce some notation, I'm going to call M sub G the moduli space of all Riemann surfaces of genus G. Most of what I'm going to say is true, but not so interesting when the genus is 1. Some things are not true, literally, when the genus is 1. So I'm going to restrict myself to the most interesting case, which is when the genus is high, larger than 1. So this is the space of all Riemann surfaces up to equivalence, up to conformal equivalence. Then I'm going to call A sub G the moduli space of abelian differentials on Riemann surfaces. And one thing that's quite useful is that these two spaces are finite dimensional. They are essentially manifolds, not quite. A sub G is an orbifold, M sub G is also an orbifold, but they are almost complex manifolds. And we can even compute, this is rather classical, we can even compute the dimensions. This one has dimension 3g minus 3, and that one is 4g minus 3. I'm writing complex dimensions. If you want to think real, just multiply everything by 2. And the space, the moduli space of abelian differentials is actually a fiber bundle over the moduli space of Riemann surfaces. So you have a Riemann surface, and on top of it, you have the space of all abelian differentials that are holomorphic for this complex structure down there. It's essentially, but not exactly, the cotangent bundle for this space. As I said, this space is not quite a manifold, and I'm cheating slightly here, but it's not far from being the cotangent bundle for the moduli space of Riemann surfaces. Now, A sub G, the space of all abelian differentials, is very naturally stratified according to the types and the numbers and types of zeros that one form has. So given M1, M sigma, these are meant to represent multiplicities of the zeros. One calls A sub G of M1 to M sigma the subset of all abelian differentials that have exactly sigma zeros, and their multiplicities are M1 through M sigma. And in order for this to be possible, there has to be a relation between the multiplicities and the topology of the surface, which is written over there. This can only be, this is only possible if the sums of the multiplicities, the sum of all multiplicities is equal to 2g minus 2. This is, you can call it by various names. You can call it Gauss-Bonnet theorem. You can call it Riemann-Roch. It's just classical fact. You can call it Poincaré-Hopf. So this is any of these sets where I've fixed the number and types of zeros is called a stratum of A sub G. And these strata are also finite dimensional spaces, and their dimensions are known. It turns out that they have lots of structure. For instance, and that's important for what follows, each stratum has a canonical volume defined on it. It has more structure. It's a complex affine space. Particularly, it has this volume measure. And we have known for 20 years that this measure is finite. Every stratum, that's the theorem of Maser and Veitch, every stratum has finite volume. It turns out that it's very hard to actually calculate these volumes, but that has been done recently, about a year and a half ago, by these people, where they obtained explicit formulas for the volumes of all strata. The numbers they get are quite curious. In particular, if you have any stratum which corresponds to a surface of genus G, its volume is a rational multiple of 2 pi to the power G. So there's very rich arithmetic structure involved here. On the other hand, the strata themselves are also interesting from the topological point of view. They are not always connected. That has been discovered by Pierre Arnoux, who gave an example of a stratum that has 3 connected components. It turns out that's the worst possible case, or the best possible case, the largest possible number of connected components. And Kontsevich and Zorich have a beautiful theorem where they give a complete classification of all connected components of all strata. That's also a rather recent fact. Now, the reason I'm introducing this notation is that I want to describe to you this dynamical system that acts on the whole space of abelian differentials, this A sub G. And it turns out that it's surprisingly simple to describe. The Teichmüller flow is, well, I've written it like this. It's just a natural action on this moduli space of abelian differentials of the diagonal subgroup of SL2R. The diagonal subgroup is a subgroup of matrices of this form, e to the t, 0, 0, e to the minus t. What it means in formulas is that the Teichmüller flow acts on a one form by multiplying the real part by e to the t, by dividing the imaginary part by e to the t, and that's it. In terms of pictures, in terms of polygons, it's even simpler to understand. You just take a polygon, you stretch it by e to the t in the horizontal direction, you squeeze it by exactly the same amount in the vertical direction, and that's it. That's what the Teichmüller flow does. It may seem to you that this doesn't, I mean, this cannot possibly be very interesting because what the action is so simple, but you should not forget that polygons are just a way to represent translation surfaces. So it doesn't mean that the surface is getting longer and longer and thinner because you can rearrange the polygon. And actually, this flow has a lot of recurrence and has very interesting dynamical properties. It's very easy from the picture, at least, to see that the Teichmüller flow preserves the area. If you have a translation surface and you apply the Teichmüller flow to it, it will have the same area because you have multiplied the horizontal by e to the t and divided the vertical by e to the t. So the area is the same. It has other properties that are somewhat more subtle to prove. It preserves, the flow preserves each one of the strata. That's not difficult either, because when you do this squeezing and stretching, you don't change the types of zeros, you don't change the multiplicities. So it preserves the strata, each one of the strata, and it's somewhat more subtle, but it's still true that it leaves invariant the volume on each one of the strata. So suddenly, we have here a whole family of dynamical systems, of ergodic systems, the Teichmüller flow acting on each one of the strata with the corresponding volume in the stratum. And this is not meant to be taken too seriously, but this is a kind of moral principle that I'm going to explore here, which says if you are able to prove a property for the Teichmüller flow, then this is a dynamical system in the space of all Abelian differentials, in parameter space. If you have a property for the Teichmüller flow in this parameter space, then it will be expressed somehow in the way individual Abelian differentials behave. Not all Abelian differentials, but almost all of them. And this is kind of a summary for the rest of my presentation. What I'm going to do is to describe two instances where this principle works. Two examples of situations where one has, where this principle can be applied. So first of all, in the very early 80s, Mather and Veach proved that not only the Teichmüller flow preserves the volume on each one of the strata, it is ergodic with respect to that volume. Ergodicity means that, well, it means that you cannot break any of the strata into two parts that are invariant, that these strata are the, I should have said, on every connected component of every stratum. Sorry. So this means that you cannot break, the connected components are the minimal positive measure sets which are invariant by the flow. So this is one property of the Teichmüller flow, and it has a consequence, and I'm not saying the consequence is obvious by no means, this is also a theorem, but it is a consequence that because the Teichmüller flow is ergodic, then the geodesic flow on almost any translation surface is uniquely ergodic. Meaning, you take almost any polygon, you choose almost any direction to move, then the geodesics in this direction will be dense on the surface, pretty much like in the case of the torus with irrational slope. The geodesics will be dense, but they will be more than dense. They will be uniformly distributed on the surface. So you start from the point Z, you start moving up around the surface. This means that the surface is getting painted black in this picture. And regardless of where you start, after a while, the whole surface will be more or less evenly painted black. That's what unique ergodicity means. And the speed at which you see this uniform distribution arising is the same, the uniformity is the same independently of where you start. Okay? So unique ergodicity means that everything converges to be uniformly distributed, and this convergence is uniform, independently of the points. So what I'm saying here, this is something that should be stressed, is that the kind of behavior one observes on the torus where for almost all slopes, meaning for all irrational slopes, the geodesics tend to be uniformly distributed, that behavior is true in general for any translation surface, at least for almost every translation surface, and moving in almost every direction. It's certainly not true for all, because, for instance, in the case of the torus, if you happen to take a rational slope, it won't be the case. It turns out that this is a rather clever application of the Mather-Veach theorem, which was carried out by Mather and Veach, but it's not best possible. There's a considerable improvement by Kirchhoff, Mather, and Smiley some 5 years later, around 1985, 86, where they got the same conclusion. It looks almost the same. That's why I highlighted this word. It doesn't have to be for almost every surface. It's for all surfaces, and then for almost all directions. So you don't need to perturb the polygon when you start. You can start with any polygon and then choose the direction with full probability, and you get unique ergodicity. So you see a statement about the Teichmüller flow in the space of all abelian differentials and the consequence on the behavior of individual abelian differentials, of individual translation surfaces. So I want to describe another, more recent conclusion, result that goes along this moral principle. And in a sense, the previous theorem tells us what is the typical behavior of geodesic flows. Typically, the geodesics are dense. Typically, the measured foliation that one gets is minimal. All the leaves are dense. That's what's typical. But this doesn't tell us much about quantitative behavior. It's just more of a qualitative kind of statement, a topological statement, and I want to go quantitative. And that's also something that people have looked at for quite some time, at least from the work of Schwarzman in the 50s. So I have to introduce some terminology. We want to describe quantitatively long geodesic segments. Now here is a trick to do that, a trick to bring in tools from topology, at least a setup from topology to do that. You take this very long segment, gamma. In this picture, it would be this line here, which I assume you agree it's very long. And we can always close it by, for instance, well, this point here, well, I could do it in various ways. I can, for instance, add a little tiny segment there to join the tip. Oh, by the way, this is a polygon, and it's like a fundamental domain, and I've drawn on the picture several copies so that you can see the long segment instead of seeing it wrapping around the polygon. So you just add this little segment here, and when you do that, now, in this particular case, this point and this point are the same after identification. So the curve that you get here, by taking this geodesic segment and then a segment more or less arbitrary with bounded length, it has become a closed curve. It can actually be deformed into this zigzagging curve here, which is also a closed curve. Deformed means that they represent the same elements of the first homology group. So summary, if you are given a very long geodesic segment, you just add a short bounded length segment and you turn it into a closed curve. So now you can see this as an element of the first homology group with integer coefficients on the surface. If you took the geodesic along a good direction, one of these for which the previous theorem works, then you know that the geodesic flow in this direction is uniquely ergodic, and that has consequences. One of them is that if you take this element of the homology, it's a vector, and you normalize it by dividing by the length of the geodesic, which is essentially the length of this closed curve, then the quotient converges to something, and this convergence is uniform. This something is an element of the first homology group with real coefficients that Schwarzman called the asymptotic cycle of the foliation. So this basically says that when you take a very, very long segment, you can more or less pretend it's a closed curve. And if you took it, the length really long, you average out the behavior of the curve by the length, you get the C1, which is essentially telling you what you have been doing in the topology of the surface, how many times you went around different generators of the homology. Moreover, this asymptotic cycle C1 does not depend on the point where you started. That's uniform convergence, unique ergodicity. It only depends on which surface you are considering and in which direction you left. It clearly depends on the direction because it's really saying what, in topological terms, what geodesics in this direction are doing. Well, so this is just a definition, but it's a bit more. We know that C1 exists. The limit exists, at least for directions on which the flow is uniquely ergodic. Now, in the early 90s, Anton Zoric started doing calculations around this notion to try to understand how, so we have this convergence, how do deviations behave? If you take a very long but not infinite segment, how close, in which sense it is close to the limit that you are going to get. So essentially, the unique ergodicity tells you that h of L divided by the length converges to C1. And the question is, what can you say about the error? What can you say about the deviation from the limit? And you realize that the answer is actually quite rich. In this picture, I'm trying to describe pictorially the kind of behavior that Zoric observed. Think of these dots as being the values of this difference, these are vectors, for a sequence of choices of the length, say integer length geodesic segments. And what he realized is that these differences are not just a random blob. They tend to align along a favored direction, which is the C1, and they behave very much like a random variable, jumping as you increase the length, jumping from one place to the other, but still governed by the fact that there's a favored direction, C2. Also, the amount of error, the size of this error, L is supposed to be the length of gamma. The error is cannot be very big. So essentially, there are two conclusions here that the picture tries to express. There's a favored direction, and the error is never bigger than the length to some power, which is smaller than 1. And also, that bound is best possible. That's what I call amplitude. So this is the kind of empirical observation made by Zoric. And it turns out that this is true for first-order errors, but then if you go for the second-order errors, they have a similar behavior. The component, if you take out the norm of a length of a gamma times C1, and then you also take out the component along C2, what's left, the second-order deviation, also has a similar kind of behavior. It has a favored direction, and it has an amplitude, which is another power of the length, a power which is slightly smaller. And you can go on like this for a while. You calculate the next favorite direction, you take out the component in that direction, and the deviation behaves in the same way until you reach the order which corresponds to the genus of the surface. And then it all stops. From then on, the deviation is bounded, independently of the length of the geodesic. So one can formulate, I like to formulate that as a kind of Taylor formula. I like to formulate that as follows. H of L of gamma, to the first approximation is C1 times the length. To a second approximation is there's a correcting term, and so on, up to the gth order, and then the rest is bounded bounded term, where bounded means independently of the length. So this is a beautiful sort of explicit formula that completely describes the quantitative behavior of long geodesics. It's not to be understood really as a sum of numbers, and it's more like a sum of random walks. But let me say what the conjecture was by Konsevich and Zorich in precise terms. So it's called the asymptotic flag conjecture, and it says that one can find numbers, nu1, nu2, nu-g, which have this meaning, and one can find subspaces of an increasing sequence of subspaces of the homology. These subspaces form a complete flag, which means that each one is contained in the other one, and the dimensions increase by 1. And this flag determines the behavior of the geodesics quantitatively in the following way. The deviation of this vector h of gamma from the subspace Li has this amplitude, and the deviation from the largest one, this is for all I less than g, and the deviation from the very last subspace, the one of dimension g, that deviation is bounded independently of the length. So it's like a Taylor formula where the error is bounded, which is much, much better than what one usually gets from Taylor formulas. Well, so the main result that I want to mention in this last part is that this conjecture is actually true. The statement is not, there are words in the statement that I didn't mention. This conjecture can be made for every stratum. What I'm saying is that the conjecture is true for every stratum. To check it for individual strata is not so difficult, but you have a discountable family of strata, and that's what the statement is saying. That this is true. You do have this quantitative description of the geodesics for all strata. And this is joint work with Artur Avila from last year. Let me just mention that there's some story to this statement. First of all, it was formulated, the conjecture was formulated by Zorich and Konsevich, and they translated it into, along the lines of what I call the moral principle, they translated it into a statement about the Teichmüller flow that I'm going to tell you what the statement is. And then, especially Giovanni Forni worked on this, and a couple of years ago, he got some fundamental progress, which included a proof of the conjecture for genus 2 surfaces. He actually did better than that. He proved that this coefficient here is never 0, and that, in particular, gives the proof of the statement for g equals 2. So just to finish, let me tell you why this fits into my moral principle. It's somewhat technical to express, but I will try to say what's the connection with the Teichmüller flow. First of all, there's this technical notion in dynamics of Lyapunov exponents. Lyapunov exponents are, well, roughly, you take nearby points, say a point P and another point which is close by in a certain direction. On the surface, in this case, it would be on the Abelian, the moduli space of Abelian differentials. You let your flow take you to the future. The 2 points tend to get either close to each other or further apart. You look at this distance after time t. It may look like the original distance. So this is after time t. This may look like the original distance times an exponential factor, e to the time that passed times some constant, and this constant is the Lyapunov exponent, is one Lyapunov exponent for the system. In general, this calculation depends on where you do it, on the point P, but if you have ergodicity, Lyapunov exponents are really constant functions, are numbers. And in the case of for the Teichmüller flow, remember the Teichmüller flow acts on a space which has complex dimension 4g minus 3. Each direction, in principle, gives you a different Lyapunov exponents, so there's a bunch of Lyapunov exponents, but it has been known that they look like this. There's a larger one, which is 2. There's a smaller one that's minus 2. 0 is a Lyapunov exponent, and then you can, they come in two series, one of positive exponents, one of negative exponents, and actually the negative ones are symmetric to the positive ones. The reason for this symmetry is that the Teichmüller flow is a symplectic dynamical system, and this symplectic character immediately implies this symmetry. There's more symmetry. There's a bunch of 1s that appear as the Lyapunov exponents here, and then the same number of minus 1s. Well, the number of 1s is the number of singularities minus 1, and they are rather well, it's rather well understood what they are doing there. And then you can see that there's also symmetry around 1 and another symmetry around minus 1. For instance, here you have 1 plus nu g, and there you have 1 minus nu g. So this existence of these numbers comes out from general dynamics theory. The fact that they have this symmetry has to do with the symplectic structure that is preserved by the Teichmüller flow. And actually, Veach proved that this inequality here is strict, so that the first exponent that appears is actually smaller, strictly smaller than 1, and so this is strict. And of course, then by symmetry, that 1 is also strict. And the work of Forni that I mentioned was to prove that this inequality here is strict. And so then, of course, the other one there is strict. This one is strict as well, and so is that one. And what Artur and I actually do for proving this, the Zurich-Kuntsevics conjecture, is to prove that all inequalities are strict, which is a fine, detailed statement about the behavior of the Teichmüller flow. And then from that on, the fact that the conclusion that you have this asymptotic flag governing the behavior of geodesics for individual directions and individual translation surfaces is, well, it's a non-trivial consequence. In some sense, it's contained in work that had been done before by Zurich and by Kuntsevics. Thank you very much.
The Abelian differentials by isomorphism.
I don't know. I mean, let me answer your first. I mean, the answer to the second question is I don't know. To the first one is maybe I have something intelligent to say. This statement, I mean, here at the end I mentioned that we proved something about Lyapunov exponents for the Teichmüller flow. It's actually not directly for the Teichmüller flow. It's for a certain dynamical system that is related to it, the Kuntsevics-Zurich co-cycle. But the way we do this is by first giving an abstract general criterion with explicit conditions that have nothing to do with all this. They really come from ergodic theory and dynamics. With explicit conditions, let's say if these conditions are met, then you plug them to your favorite system, and it comes out that the Lyapunov spectrum is simple, which is this statement. Okay? Then the second part of our proof is to take this criterion and check that in this particular system it is satisfied. So the answer to your first question is probably yes. The conditions are rather easy to satisfy. They are transversality conditions, generic conditions, saying that subspaces are in general position to one another. So it's very likely that in any system you are interested in, they may be satisfied. But in any case, it's doable. I mean, you can at least check whether these conditions are satisfied. So the general criterion might be useful in more generality. But I mean, I don't know what models you have in mind. Oh, yeah. Oh, yeah, they are extremely interesting. They are not known. I mean, there's still a lot of mystery. There are explicit formulas for all of them, but the formulas tend to be big and not very illuminating. But there's a lot of, for instance, there's a conjecture by Zoric and Koncievich, which says, according to which, for every stratum, if you calculate nu1 plus nu2, nu1 is 1, plus nu2 plus nu-g, this should be a rational number. Well, it turns out that for certain surfaces of genus 2, that's false. So the conjecture is, except for genus 2. The explanation, believe it or not, the explanation is, they give is that, well, the first one is 1. So to ask that the sum of the first two be a rational number implies, doesn't give much freedom to nu2. So that's asking too much. But if you have 3 or more, that's okay. So this is, Zoric knows certainly more about these numbers than is written in the papers, but yeah, they are very interesting. They depend, exactly, they depend only on the stratum. Yes. The subspaces, you see, these numbers are the same there. They are the Lyapunov exponents. Since the Teichmüller flow is ergodic on the stratum, these are numbers that depend only on the stratum. The flag is a different thing. In particular, it includes the direction of the asymptotic cycle. So it has to depend on which direction they're taking. They can also be understood, the flag can also be understood in terms of Lyapunov exponents and Lyapunov subspaces in ergodic terms. It's not mysterious. But these numbers are really interesting numbers with very interesting arithmetic properties.
Well, genus 3 is quartic plane for
You should tell me.
So, is there any correlation to the, say, stratification regarding the flexes or bitangent lines, which in a sense correspond to
I don't know.
canonical?
I lack the terminology to answer your question. I would like to discuss it with you. Let me just say that for genus 3, one gets, I mean, one doesn't get all the surfaces in this way. There are constraints. But for genus 3, one gets some surfaces which are not hyperelliptic. And hyperelliptic surfaces are everywhere in this business. But already for genus 3, there are some non-hyperelliptic surfaces that come up for certain strata.